Hello everyone, welcome to my group theory lecture. So in this lecture, we continue to study examples of groups. Okay, so we begin with the matrix groups. Okay, as the name suggested, we're going to talk about certain groups, whose elements are given by matrices. So the first example here is the set of, the set here, this notation, right? M sub little m times little n of R. So this set is the set of all m little m by little n matrices, okay, of real entries under matrix addition. Now this set with the matrix addition becomes an abelian group of infinite order, right? So this m by n means that the number of so m is right. So these are the matrices with the m rows and n columns, right? So m is the number of rows and n is the number of columns. Okay, next one is another important example. I think I don't know, if I remember correctly, I think I mentioned about, this group, right? Uh, I think it in my introduction, but it's okay. The set G sub L, okay? No, the set GL of N R. This is the set of this notation is means denotes this denotes the set of n by n. These are square matrices, right? Not only that, so the number of rows and number of columns are the same, but not only that, these are n by n non-singular matrices of real entries under matrix multiplication. So we consider matrix multiplication here. By the way, non-singular, if you forgot about it, or if you are not familiar, what that means is it's invertible. Okay, these are the non-singular matrices are matrices, square matrices that are non invertible, and invertible means it has right. So a matrix is invertible means that that matrix has an inverse matrix. Okay, right. So obviously we have to require the those guys, members of this GL of n R to be non-singular, so that it can be a group, right, under matrix multiplication. In fact, this guy GL with the matrix multiplication is a non-abelian group. Okay, non-abelian group. Well, you can easily guess, as you learned in linear algebra, matrix multiplication is in general not commutative, right? So it is a non-abelian group of infinite order. GL of NR is called, the general linear group of degree n. Okay, general linear group of degree n. As a matter of fact, the reason we specify, R, the set of real numbers, is that, R can be replaced by, say, for instance, like, the, uh, the set of all complex numbers, okay? Right, or actually, we can consider more general, the general linear group. Okay, more general linear group. In fact, this R can be replaced not only by C, the set of all complex numbers, but also, it can be replaced by just a field, right? A field. In case if you are not familiar with the field, probably if you are studying group theory, most likely you are not familiar with the structured field. That's okay, right? You don't have to worry about that. Anyway, also you can easily see why we are using this notation, GL. That's for general linear, okay, general linear. And in fact, it can be viewed as the set of all linear isomorphisms, all linear isomorphisms T from R to the power N, onto itself, R to the power N. All right. So those are. There are, many more important like matrix groups. All right, but those are the, starters. Okay, here comes another important example. Klein four group, or in German that's Vierer-Gruppe. Okay, so Klein four group. You are seeing, in fact, a picture, a rectangle. Okay, a Klein four group can be obtained. Okay, is obtained by considering like rotations, right? Rotations. So we are considering actually three axes. So x-axis, okay, x-axis. So rotation, about the x-axis by 180 degrees. That's, we call it A. Here you see B, right? So B is named for the rotation about y-axis by 180 degrees. And then, we also see, the rotation C. What is that? You imagine that there is an axis coming out of this origin, okay, coming out of this origin. Well, you might call it the z-axis, right? Z-axis. So again, like a rotation about this z-axis coming out of this origin, right? By also 180 degrees, okay, 180 degrees. So that's C. So each of the rotations, A, B, and C, like I just mentioned, that's 180. And those three rotations, A, B, C, satisfy the following relationship. Okay, so A squared equals B squared equals C squared is E. E is what? Identity. E is the identity. A times B equals B times A equals C. B times A equals C times B equals A. And C times A equals A times C equals B. So what does it tell you? It tells you that Klein four group is an abelian group. Okay? Oh, I have not mentioned what Klein four group is. So I was a little ahead. Anyway, here the multiplication is a successive application of rotations. Okay? So successive application means, the functional composition. Okay, functional composition. So here, the set V consisting of E, A, B, C with, this successive application of rotations as a multiplication is an abelian group of order 4 called the Klein four group, or in German, Vierer group. Well, the reason it's got the actually German name is because, this the Klein four group is named after, the German mathematician Felix Klein. Okay, Felix Klein. There is another way we can represent it. Okay, we can represent it. The Klein-4 group, actually members of Klein-4 group. Okay, so by labeling the vertices of the rectangle as 1, 2, 3, 4, we can define each rotation as a permutation. Okay, as a permutation of 1, 2, 3, 4. Remember the word permutation. Here, a permutation of 1, 2, 3, 4 means that a bijective map from 1, 2, 3, 4 onto itself. That's called a permutation. All right? So E equals 1, 2, 3, 4, 1, 2, 3, 4. Obviously, 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4. So nothing happens, right? That's the identity. The rotation A is what? 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3. How do we get this? Obviously, from the definition. So here, that's rotation A, right? So, if you rotate this rectangle with respect to, about the x-axis, right? By 180 degrees, Then this 1 goes to 2 and 4 goes to 3. Okay? So the, labeling becomes 1, 4, 3, 2, right? 1, 4, 3, 2. Okay? So that's how we got that permutation. And, B and C, the same. So I'd like to show you, how actually, so, earlier, when we defined, the Klein-4 group, we used the geometry, right, in terms of rotations. But by labeling the vertices of the rectangle, okay, so as 1, 2, 3, 4, we represent each member in terms of permutation, right, in terms of permutations. So that way, actually from the geometry, we can move from geometry to algebra. So in fact, without having any consideration of the rotations, we can simply just do everything with the Klein-4 group, as algebra, okay, as algebra. So we can in fact multiply. This can be done. This can be done also by geometric consideration. Okay, geometric consideration using rotations. But we can also purely get this. So AB equals C we can do purely by calculating the multiplication of the two permutations. Okay, so let me show you this. So I'm gonna get to my notepad. Okay, so we are talking about here Klein. So example, right? Example. Klein. Four group. Okay, Klein-4 group. So A, in terms of permutation, right? So we have a rectangle here. I think I better use draw rectangle. Oh, okay, that's cool. That's rotation A by 180 degrees, right? That's rotation B by 180 degrees. Excuse me. And also in mathematics, unless otherwise specified, the rotation is always counterclockwise, positive rotation. So counterclockwise rotation, positive. Clockwise rotation, negative. Okay, right. That's convention. It's not why we are doing it, but that's just the convention. People decided to do that. Okay, so A in terms of permutation. So 1, 1, 2, 3, 4. So we talked about it, right? So we're gonna label this as right, 1, 2, 3, 4. So when you rotate about the x-axis by 180 degrees, 1 goes to 2, and the 2 goes to 1, right? 2 goes to 1, 4 goes to 3, and 3 goes to 4. So we get this 2, 1, 4, 3. And the rotation B, if you rotate this, about y-axis by 180 degrees, right? So 1, 2, 3, 4. So 1 goes to 4, right? 1 goes to 4, 2 goes to 3, and 3 goes to 2, 4 goes to 1. Okay, so we get this permutation. So we want to calculate A times B. A times B. So that's 1, 2, 3, 4, 2, 1, 4, 3 times 1, 2, 3, 4, 4, 3, 2, 1. Really, you can calculate immediately, okay? From this, you get the product. So here, again, here multiplication is a successive application of the rotation, right? Successive application of rotations. Also, in other words, algebraically, that's functional composition, right? I mentioned that also, functional composition. So here, 1 goes to 2 and 2 goes to 3. So composition is 1 goes to 3. 2 goes to 1. Okay, here 1 goes to 4, so 2 goes to 4 when as a functional composition, right? So you can easily actually get it at once. Or, another easy way to do is the following. So you write the first guy, 3, 4, 2, 1, 4, 3. So this stays same. And I'm going to rearrange the second guy, okay? So instead of 1, 2, 3, 4, first row, I'm going to write it as a 2, 1, 4, 3. So here, then you have to change it accordingly, right? So 2 goes to 3, so this is 3. 1 goes to 4, 4 goes to 1, and 3 goes to 2. So as a functional composition, this becomes 1, 2, 3, 4, and that's all you have to write is this guy here, right? That's going to be 3, 4, 1, 2. And that should be rotation C. The C is a rotation about this 100 rotation about the z-axis, right, which is sticking the axis which is sticking out of this origin, right? So that's C. So when you rotate this by the 180 degrees, what happens? The 4 goes to 1. No, I'm sorry. By 180 degrees, right? That would be 4 goes to 2. Okay, 4 goes to 2. Yeah, so 4 goes to 2, and 2 goes to 4. 1 goes to 3, and 3 goes to 1. Okay, so 3, 4, 1, 2. Right? Okay, 3, 4, 1, 2. That's what we have. So that's equals C. Okay, so moving on. The next example is, by the way, these are all important examples of groups. Next one is the nth dihedral group, okay, which is denoted by d sub n for n greater than or equal to 3. So let us consider an equilateral triangle. So that means what? Triangle with all three sides same. Okay, same length. Having same length shown in the following picture. So we have an equilateral triangle, and we are considering 3 rotations. Okay. So here, 3 rotations. They are called rho, mu1, and mu2, and mu3. 4 rotations. I'm sorry. There are 4 rotations. Rho is counterclockwise rotation about the axis coming out of the origin by 360 divided by 3. So each rotation is by 120 degrees. Mu I equals 1 to 3 is counterclockwise rotation about the axis of rotation through each vertex I by the 180 degrees. So here, right? That's mu1, mu2. So actually that axis go through, the origin, right? Origin and 1. And here same, going through the origin, right? Here, going through the origin also. So maybe I should have also mentioned that too. Rotation through each vertex I and the origin, right? That's the axis. As permutations of the vertices 1, 2, 3, right? Rho and mu I are given by the same way, okay? By these permutations. And in this case, the nth dihedral group, okay, the nth dihedral group, d sub n, actually D3, we are talking about only D3 when n equals 3. So there are 6 elements, okay? So D3, E, rho squared, mu1, mu2, mu3. This forms, a group called the third dihedral group. And in fact, since I showed you the permutation representation of each element, right? Each rotation, so you can easily do the operations, right? Again, here the operation multiplication is the same. Successive applications of rotations. So anyway, you can easily check that. Mu1, mu2, that's rho squared, and mu2, mu1 is rho. These are not the same. So D3, not like Klein 4 group, D3 is not an abelian group. And D3 is in fact a group of symmetries of an equilateral triangle, as you saw earlier, right? So geometrically, D3 is the group of symmetries of an equilateral triangle. Okay, so next one we want to talk about. Let us consider a square as shown in the following picture. So what I am going to consider is when n equals 4 case. Okay, when n equals 4 case. So let us consider a square as shown in the following picture. Okay, this square here. So we see the rotations, right? So we have a rotation rho, mu1, mu2, and delta 1 and delta 2. Okay, so what are they? Rho is counterclockwise rotation about the z-axis coming out of the origin by 360 degrees divided by 4. So, each rotation is by 90 degrees. Okay, 90 degrees. Mu I equals 1 and 2 are counterclockwise rotations about the y-axis and the x-axis respectively by 180 degrees. Delta I for I equals 1 and 2 are counterclockwise rotations about the axis through vertices and 2, 4. Not just that. Oh, actually in this case it's vertices 2 and 4 and the axis through the vertices 1 and 3. Okay, so I correctly stated and respectively by 180 degrees. Okay, if I go back, right, 1 and 3, that's delta 2, 2 and 4, So x is going through vertices 2 and 4, that's delta 1. And likewise, we can write down each of these rotations as permutations of the vertices 1, 2, 3, 4. So here are those, the permutation representations of each rotations. The rotations. Okay, rho, mu1, mu2, and delta 1, delta 2. D4 is the set consisting of E rho squared, rho cubed, and you can check rho to the power 4 becomes E again, okay? And that's why, it includes only rho squared, E, rho cubed, mu1, mu2, delta 1, delta 2. Okay, so that's, and so, this set with, again, multiplication, which is a successive application of rotations, all right, forms a group called the fourth dihedral group. So this is a group of 8 elements, and geometrically, this is the group of symmetries of a square. It is also called the octic group, okay, octic group. Obviously, because it's got 8 elements. Although, I should warn you that this is not the only, the group which has, the 8 elements, but this particular one, fourth dihedral group, that's octic group. Okay. For instance, like Z8, Z sub 8, that also has, the cyclic group that has 8 elements. Well, we don't call it, the unoctic group. Okay, so here also I'm calling it the octic group. So this particular one is also called the octic group. In general, note that the order of D sub n is 2 times n for n greater than or equal to 3. All right, folks, so this is it. More details of my discussion here can be found in my lecture note at the following address. Again, as usual, okay, this is a long address, but it's a hyperlinked. So all you have to do is just click on it, and it'll take you to this note. Okay. In case, as usual, in case if you want to visit my main Blogger site, just click on this word Blogger, okay, which is also hyperlinked, and it'll take you there where you can find also many other lecture notes of mine. And also, there's a problem set available for this, the discussion, right? Examples of groups. That problem set is available at the following address. Pretty, again, long, complicated, but not a problem. It is hyperlinked, so you just click on it, and it'll take you to the problem set 2 at my Google Drive site. Okay, thank you very much for listening and watching this lecture. Bye-bye.